Welcome once again to the fourth lecture of the first week. It rains outside, it's really interesting thing to give lecture, and this time inside my own office. You must be observing the difference between the length of the boards compared to the first two lectures, which was in a studio. Here it's in my own office at the Indian Institute of Technology, Kanpur. So here is the topic of today's lecture: optimization models in finance. Okay. Now, optimization is the science, art and mathematics of choosing the best among a given amount of things by following certain principles or laws, or based on certain conditions. So, in financial models where risk is involved, we tend to use optimization to model our problems. So, let us first write down what is a basic optimization model. So, I am writing it in the most general mathematical form. So, by an optimization model we usually mean either to minimize or maximize. I am more habituated with writing minimize, because maximize is nothing but minus of mean of minus of fx. So, maximize over subject to means we will be in our discussion considering the case where x belongs to a finite dimensional space Rn, and let us tell you what is this x and c and all those things. So, x, of course, it could belong to any general vector space. It could be in infinite dimensions. In many situations it is in infinite dimensions, especially in the more deeper analysis of risk, and such research has come out very recently in the last 10 years, and here we will be largely concerned where x is in Rn, is a vector in Rn, and x is called the decision variable. This x is what we have to find out. This set C, which is a subset of Rn, is called the feasible set. That is, consideration of any x which is outside C is not really relevant to this problem. And f is called the objective function, the functional value that you want to minimize. Of course, you have heard about minimization, maximization, you have done such problems in your first year calculus courses or even higher secondary classes. But here we look into the subject optimization as a standalone mathematical discipline which we analyze in a more detailed way. So, here is a basic structure of an optimization problem. Now, if C is equal to Rn, that is the whole space, we say then the problem is unconstrained. That is exactly what you learn in your high school, and where high school C is equal to R actually, and n is 1, and in the first year you can learn about n is 2, 3 like this. And when C is a proper subset of Rn, that is C is a subset of Rn but C is not equal to Rn, then the problem is a constrained problem. Constrained problems are of course harder, and in finance we have to deal essentially with constrained problems. Of course, here C is just an abstract set. It does not allow us to do much operations on C. So, in general, C has a more detailed form. So that what provides me with a standard form of an optimization problem. Our aim here today is, after we discuss the standard form, that we essentially tell you about some important classes of optimization problem and show 2 examples from finance how we can actually model the thing using optimization. So let us observe this, that now let me write down C as a set of all x in some capital X, which is subset of Rn, such that Gix is less than equal to 0 for I is equal to 1 to m, and Hjx, so these are functions so I will only consider an x, a vector x in Rn to be in the set C if it belongs to this given set X and also satisfying all these inequalities and equalities simultaneously. So now the problem, this problem, which I can now write as problem P. So the problem P in the standard form would look like minimize f of x subject to Gix less than equal to 0, I going from 1 to m, and Hjx equal to 0, j going from 1 to k, and x belonging to capital X. So this is one of the most standard way of writing an optimization, a general optimization problem. So these Gix, these are called inequality constraints, Hjx are called equality constant, and this is called an abstract constraint. Inequality constraints, and these are called equality constraints. And this is called an abstract constraint. Of course, you can say that you have not got rid of this abstractness of C, you have plugged in that X. Yeah, but in most of our applications, this abstract constant X would be Rn plus, so which would simply mean that X is a vector whose all components are non-negative. Sorry, abstract constraint. So once that is done, I hasten to add that. So once that is done, I hasten to add that now I will start discussing various classes of important optimization, various important classes of optimization problems like linear problems, linear programming problems, or linear optimization problems, quadratic optimization problem under linear constraints, and quadratic optimization problem under quadratic constraints. So the type of problem that arises in finance, and also some class of problems very hard actually, called integer programming problems. So here, if I let us look into this whole thing. So here, by choosing very particular type of f, very particular type of f, right, very particular type of g, very particular type of h, very particular type of x, we go to certain special classes of problems. The type of problem which the finance world usually deals is called a convex optimization problem. The convex optimization problems arises when f is convex, gi's are convex, hj is affine and x is usually a closed convex set. So in this case, on the problem P, which is now our standard problem, we will now call this as P, forget the other thing. We will be essentially dealing only with this structure. So for this case, so we will have f and gi to be convex. Of course, it goes without saying that both f and gi, if you are functions from Rn to R, that is a statement which I had not made in the last statement, in the last description of the general problem, but f was there a function from Rn to R. Of course, because if you do not have the real values, what are you going to compare? I here assume that you know the difference between a local minimizer and a global minimizer. So those who do not know the difference between a local minimizer and global minimizer, just Google it and in Wikipedia and check the definitions, or you have huge number of stuff on optimization on the internet. So you can really know the difference, and I wouldn't like to repeat the difference because I would rather go into the issues in finance. So here, so these are convex. So I am just writing in general a function phi from Rn to R is convex if for any xy in Rn, phi of lambda x plus 1 minus lambda y is less than equal to lambda phi x plus 1 minus lambda phi y for all lambda belonging to 0, 1. This essentially says that if you draw the curve or the graph of a function, if you just take a function from R to R and you just draw the graph of a function, it should look like this, which essentially says that if you shade the area of the graph, which is called the epigraph, the epigraph must be convex. A function is convex even only if its epigraph is a convex set. So a convex set is a set where if you take any 2 points and join them by a line segment, any 2 points on the set and join them by a line segment, that line segment lies inside the set. So we will not go into this detail. This also means that if you take this straight line, this graph of a convex function, and if you join them by if you take 2 points on the graph of a convex function, if you join them by a chord, then this chord always lies above the graph of the convex function. So this is a very, very important idea, very, very important geometrical idea. This is essentially a geometrical idea. Now, important examples of convex functions are phi x is affine or linear, say a of x, where a is given in Rn. So this is called a linear function. So linear functions, I am sure most people would know about linear functions, that a function f is linear if f of x1 plus x2 is equal to f of x1 plus f of x2 and f of alpha x is alpha of fx for any alpha. So this ax is actually the standard dot product, which simply means if a1 into a dot 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 an is the components of the vector a and x1 x2 xn is the components of the vector x, and then this is nothing but this quantity, which is nothing but the extension of the notion of multiplication. So another class, so if you add another real number to this linear function, then what you get is called an affine function. So b here is in R, and what you get is an affine function. Another, so these two functions are also, these are all examples of convex functions, special class of convex functions. So if the function f is convex, gi's are convex, hjx are affine, these equality constants have to be affine, and this is a closed convex set or just a convex set, then we call this problem as a convex optimization problem. So here, for example, another important class of convex functions is that of the quadratic form. XQX, so this is a quadratic form, and this Q must be positive semi-definite. That is, this quadratic form must be always greater than equal to 0 for any x in Rn that you choose. Must be positive semi-definite. Of course, in this just 1 or 2 lectures you cannot do justice to a huge subject called optimization, but this is just to give you a basic idea, because all these type of class of functions will start playing a role in finance, specifically the quadratic one, because this will, in the Markowitz portfolio optimization model, this quadratic form would represent the risk, because variance of a random variable can be expressed in terms of a quadratic form, and that would be convex. Okay, and now we will now write about linear programming problems. We will also write about quadratic programming problems. So we are now going to start talking to you about linear programming problems or linear optimization problems. There are a lot of books which deal with linear optimization problem, where we minimize Cx which is nothing but C1 x1, C is in Rn of course. Subject to Aix minus Bi is greater than equal to 0. So it's a equality constants of the greater than equal to type. You can represent it in the same way. You can put By minus Aix less than equal to 0, I equal to say 1 to m, and each of xi is greater than equal to 0. This is same as writing x element of Rn plus. So this is the standard, the canonical form of a linear programming problem. This is what is called a linear programming problem, sometimes written as LPP, linear programming problem. So this is a very important class of problem, and in finance in many cases this is quite a standard thing which will appear. It may or may not appear always, but it will appear in many cases. There could be another case where you can write this as minimize Cx subject to Aix, or you can just write Aix greater than equal to Bi if you feel that that is more comfortable, but looks nice rather than writing this way. It might look a bit clumsy. Books usually would write it in this way, and then you can say the xi may not be all greater than equal to 0. It could be just the integer 0 or 1, or it could be that xi belongs to z plus, that is only it belongs to positive integers or non-negative integers. So this is, I am just giving, it is not that it is always either this or this. or it could be x size, could be any integer. So this sort of problems sometimes are called integer linear programming problem or linear programming problem. Let me tell you that the linear programming problem is a convex programming problem, while the integer linear programming problem is not a convex programming problem. Why convex optimization problems are important? Because for a convex optimization problem, every local minimizer is a global minimizer, and we are searching for global minimizer. But for non-convex problems, local minimizers need not be global minimizers, and that is the major issue. So this is, so instead of writing integer linear programming problem, this is what we will call as integer programming problems. Now we come to the two classes of quadratic programming problem. So the portfolio optimization problem that will start in the next lecture would essentially consist of quadratic programming problems. So the type 1 is quadratic programming problem under these sort of affine constraints or linear constraints, whatever you want to say. So you minimize a quadratic convex function, Q is positive semi-definite, plus an affine thing Cx plus D, subject to the same thing. Here xi greater than 0, I would of course go from 1 to m, or rather I should write this as ajx, maybe that is better, so that you don't confuse among the index. So this is called a quadratic programming problem under affine constraints, or in short QP, quadratic programming under affine constraints. And this is a portfolio optimization problem is actually of this form. So these are the main classes of type of problems that we will essentially deal in finance. You could have also these replaced by quadratic constants of this form less than equal to 0, but still I do not really bother much, because we won't be able to have the occasion to discuss such issues. So for our discussion this is enough, these problems are enough, and now we are going to show examples of how to model problems in finance with these sort of classes of optimization problems. So if Q here is positive semi-definite, then this programming problem is a convex programming problem, or it is not if Q is not a positive semi-definite matrix. So here, so we will be looking at the capital allocation problem. So capital allocation problem is divided into two parts. One is called the capital budgeting problem, so basically suppose capital budgeting is that, okay, you are a funding agency holding a lot of fund, a given amount of fund, and that you have to say fund scientific projects. So how will you find how much you will allocate to which project would actually be given any funding, which project would not be given any funding. So that problem is called the capital budgeting problem. And the second one is called the portfolio problem, which essentially is linked to the allocating your given amount of money for buying the shares of various stocks or various financial instruments available in the financial market. So when portfolio optimal problem is capital allocation linked to portfolio securities, or not always with securities, but it could be linked to risky securities, but could be linked to bonds, etc. So portfolio optimization problem linked to securities, what we will study in detail in next lectures. We will have 2 lectures on portfolio optimization compared to the capital budgeting, which really doesn't look at traded assets. Capital budgeting problem is allocation of a budget between non-traded assets, just like allocating budgets to scientific projects. So which our scientific organizations like DST, etc. keep on doing from time to time. So let me now give you an example of the capital budgeting model, and let us see what happens. So here, now suppose I am a scientific committee and I have M budgets to myself. My M budgets been presented before myself. I am the funder, and I am going to now decide what I am going to allocate. So here we will analyze and show that such a problem of allocation of funds for say scientific projects can be modeled as a integer programming problem of this type. So now we are going to talk about fund allocation to projects. So now there are M projects. I is equal to 1 to M, and each project has a benefit BI. BI is usually the net present value. What is BI? What is the BI? Benefit of the project I. So what is the meaning of the benefit of the project I? It means every project would have a cash flow stream associated with it. So I have an initial budget which would be a negative cash flow from my side, and then it will reap benefits which will be a positive cash flow. So this difference between the positive cash flow, the present worth of the positive cash flow minus the present worth of the negative cash flow, which is the negative cash flow itself, is called the net present value of any project. So that difference is called BI, which basically this is nothing but the net present value or NPV. Let CI be the initial cost of a single project, and I have a budget allocation. So C is my total budget. And CI with the initial cost to start project I. So that is what I am supposed to pay to project I if I have to start. Now what is my objective? I want to have a scenario where my benefits are maximum. I only give it to those projects where I have maximum benefits. In fact, a government does this on a regular basis, this capital budgeting. So my problem would be to maximize my benefit. So xi is the variable. Now suppose xi is the variable which denotes either 0 or 1. So if xi is equal to, so xi is a 0 1 variable, 0 or 1. So if xi is 0 means I do not give any money to project I. If xi is 1, then I give the money ci to project I. So my problem now is to solve this. I want to maximize my benefit. So if the project I is selected, then it gives me a benefit BI. If the project I is not selected, it gives me a benefit 0. Subject to the fact, if project I is selected, I have to pay CI. If project I is not selected, I have to pay I do not have to pay anything. So again Ci Xi, but this cost cannot be exceeding C. This cost cannot be exceeding C, and of course Xi is 0 or 1. So this is what is called the capital budgeting model. It is in the form of an integer programming problem. Now we are looking into portfolio selection problem and portfolio of bonds. We will not go into portfolio of securities, because that the Markowitz model of mean variance portfolio analysis would be dealt in detail. So we will not speak about this right here. So portfolio of bonds, that is how much bond I have to buy in order for me to trade them, buy, so that in order for me to generate the funds with respect to which I can carry out my financial obligations. Suppose I have a pension fund. And every 6 months I have to make certain payment. So let my payment vector, so I have to make that payment for say n period of time. So these are the cash flows that I will go from me. So starting from now, in the first 6 months I will pay Y1, then I will pay Y2 in the next 6 months, then Y3, Y4 and Yn till some given period. So that is my promise. So if it is a pension fund, I will make this amount of payment, right? It could be to one person or to aggregate of person, does not matter. So how will I actually go about keeping my financial obligation or keeping the promise of my financial obligation? I will go and buy bonds. Bonds with coupon or without coupon does not matter, but bonds with coupon is essentially fine. So I will go and buy some bonds, and I will go and buy some M bonds. So buy M bonds, which are indexed by J. J would denote a bond. So there are M bonds in the market and I buy them. So each bond J gives me a cash flow, say at the 6 months from now, this is giving me C1J, from further 6 months is giving me C2J and CNJ. So this is my cash flow given by the bond CJ. My question would be, what is the number XJ of bonds I should buy? So what is the number of bonds XJ I need to buy? That is exactly the question that I really have to answer. That's the issue. Now, how will I get that number? Now, PJ is the amount of money I have to pay to buy a unit of bond J. So the total money that I want to spend to buy all my bonds is PJXJ, where J is equal to 1 to M. So buy M bonds, but I want to minimize this. I do not want to pay so much. But this I have to do subject to the following, that Cij xj, j is equal to 1 to m must be greater than equal to yj, and xj, then amount of bonds is greater than equal to 0, I is equal to 1 to m. I will explain this. So what it means, that at time say t I equal to 1, right, I equal to 1, that is the first 6 months, from now the first time I am making the payment. So there I have got money from all the M bonds. So from the first bond I have got money C. So J is, so what I have got, From the first bond I have got money C11. From the second bond I have got a cash flow C12. From the third bond I have got a cash flow C13. This is the first one cash flow. So mth bond I have got a cash flow C1m, and each of them I have bought x1, x2, x3, x4 quantities. So I add them up. So in the first one, this is the amount of cash, or this is the amount of cash I get from the cash flows from all the bonds I have bought, and this cash flow must be at least equal to the amount my financial obligation, and all these xj's that I buy must be greater than equal to 0. So what we now get is absolutely a linear programming problem that we have studied. So here is a linear integer programming problem, here is a linear programming problem. The quadratic programming problem under affine constants is exactly what is a Markovich portfolio model, which we will study in detail later. In the next class, we will talk about how to analyze an optimization problem and what we can do with it. So we will discuss that in the next lecture. Thank you.